let's pi x given y, right, be the density of x given y, right? That means we already know a value of y, the density of x given y. That's a given y. Then pi of xy given y. So remember, this is conditional, right? It's highly connected with the conditional density can be written as pi of xy divided by pi of y. Now this is actually, you can think about this is actually a pre-base formula, but you know, we can avoid base formula as well if we want to. It's quite, and the proof, I'm gonna ask you to do homework, okay? Homework here. Use Kolmogorov, right? Kolmogorov. I'm sorry, so tight here. Proof here, homework, right? Use Kolmogorov. Remember that the Kolmogorov says that P, the probability A given B is equal to the probability of A intersect with B So you can use Kolmogorov formula to actually prove that Bayes theorem easily by using infinitesimal, right, arguments. So check out whether, so that is what we have there is actually direct consequence, right? Okay, so the Bayes formula typically, right, so therefore we also know, right, pi of x given y equal to pi of x y pi y. So we also have the pi of y given x is equal to pi of xy pi x. And from these two, you see that they share the same numerators. So we immediately see that the pi of x given y is equal to pi of y given x pi x divided by pi y, right? So this actually the real Bayes formulas, right? Bayes theorems or Bayes formulas. So Bayesian statistics is actually based on this formula. Okay. All right. So it's just a little bit quick. So actually, the conditional density and conditional expectation itself is very nice, right? It's actually there's a whole a few lectures a week to actually understand a conditional expectation in really deep, right? And that's going to be a basis for martingales, right? But then backward martingales. Again, I just give you some indication here so that you can learn more. This is not everything, right? So conditional expectations and then lead to martingales, right? And martingales, the best way to prove, or for me, think that the most elegant way to prove the laws of large number is your backward martingales, right? It looks beautiful, and then Kolmogorov 0 and 1 theorem, but we're not going to prove, right, the laws of large number. We're going to actually directly use it, but I'm going to state it for you, okay? All right. So let me actually. There are more definition of variance, covariance, and so on and so forth, right? But let us skip that. So how about this? We're gonna take 10 minutes break, And then we talk about large numbers, and then we talk about stochastic gradient, and then we prove, right, for the next 2 hours. Okay, so our main goal today is to prove, to state what stochastic gradient descent, how it look like, right, and then prove that it converge. Okay, so that's our main point, because that is the main workhorse of any machine learning method, right? And in particular, deep learning. All right, I see you in 10 minutes. Okay, so let us restart. So I think we have, we pretty much have what we want, but I like to have one more, right? One more. One more thing. Why now? When we introduce the conditional expectations, I'm sorry, conditional density, right? We can write the expectation, that expectation in one more different form. The reason I introduced the conditional density here is just to do we have, right, as a consequence, as a result. As a result, we have and we're gonna use this later. There is expectations of two variables, right? It is equal to xy, right? We just rewrite that dxy dx dy. But if I use the conditional expectation, then I'm sorry. We have double integral here. If we use conditional expectations, then we actually can separate thing out, right? We're gonna separate thing out. We can do expectation with respect to y first. Y. I'm sorry. I'm sorry. Let me do this. I'm sorry. We're gonna do conditional expectation with x first. And then we do dy, right? Okay, so if we can think about this way, we can write either the expectations of x, right? Expectation of x, given y, right? And then we do expectation of y, right? This is expectation with respect to x, expectation with respect to y. Okay, so so we can always do this, right? Of course, this we say x and y, but we of course we have much more generic, right? What much more generic, the expectation of any functions as a function of x and y. We can do a same way, right? This is expectation with respect to we can do expectation with respect to x first of f of xy. When we already know y, right? Given y, that means we already know y. And then we can do expectation of y after that. So there are many names for this, right? There are many names for this, but and I list a couple of names. Some of them you know, some of them you may not know, or you none. But it's I put down a name here for you, right? So this is total expectations. Remember, right? Really remember that we have a total form total. This is known as, right? Known as. There's known as a few names. Known as depends on where we are, right? Known as the total expectations formula. So recall, right? My connection with like total probability C also. the total probability that we learned, right? Last 2 days ago, total probability formula. They are very same nature probability formula. Right, and remember that in fact, the total expectation you can recover the total probability formula if you replace f with 1, right? If f is equal to 1a, right? Remember that we can always make f can be anything, right? Any measurable function here, in particular an indicator function, right? If you put down indicator function here, then we actually recover the total probability formula that we seen 2 days ago or 3 days ago. And this is also, if you do a more mathematical way, you can think this is just a Fubini, right? It's just a Fubini theorem. And if you actually even more deep into the probability theory, this is kind of this integration, right? This is a special formula of this iterations. I would say much more general than Fubini. So, and in fact, Fubini is actually a special case of these integrations. Okay, so I put down name there so that, if you want to make connections with what you know or you want to learn more, right? And actually, this integration theory itself is beautiful. It's a very beautiful theory. Actually, we use this integration to develop a new statistical inference approach, right, in our research as well. So it's very, very nice things to know as well. But it's a little bit more math involved, of course. Okay, so that's enough for expectations. Any questions? Okay, so when I say enough, it's just we actually scratch the little surface of probability theory, all right? So I hope that you actually take this and then do more. Okay, so the next thing is the laws of large number. This is the next important items that we need to cover, right, today. Okay, so we're gonna do the laws of large numbers, but before we do the laws of large number, I can give you a little bit of motivations, right? And this is how we should make connection. Like I said, right, do always make connection with what you know, and that's where you learn much more effective way, right? And transfer learning, remember that, right? We use what we know to learn something that something new, right? That much easier, right? Incremental learning is much easier. Okay, recall, right? Recall. I'm gonna actually recall here. I'm not gonna jump into. We're not gonna jump into a large number immediately, right? Because it's not intuitive, unless we go through something much more fundamental here. Recall. If I have S1 dot to Sn, it's real numbers. I have a sequence of real numbers. So what is the average? Right? Recall, then the average is given as So what is average? Can somebody tell us what is the average of n numbers? Very simple question. Trivial. What is it? Can somebody help us? Yeah, thank you. Si, I from 1 to n, and this is important, right? So like I review elementary math, not even middle school math. This is elementary math. This is actually I remember because at least in the U.S., typically in Asia we learn much more math in elementary school or middle school, right, and high school compared to America. So this is even in America. This is elementary, right? So maybe this is in preschool for Asia. So let's do preschool first. All right. So it sounds easy, or everybody understand. Now I'm going to ask you a question, right? That's a sequence, right? Or a sequence number. Now, I'm going to look at the function question now. Functions. Four functions. F from A, B to R. What is the average of F? So this is actually not elementary school. What is the average of F? How do we define? How would you define an average of a function, right? And by the way, the function is nothing more than, you see that, right? The tie relationship between is that you see that this is by itself a function. The sequence that I show you by itself is a function. It takes natural number 1, 2, 3 and return n numbers. And that is from function, it's by itself. But it should take discrete value and return discrete values. Our function here take continuous value and return continuous value. So it's a direct generalization of that. It's not, they are not separated. That is mathematically the same thing. Function. This is how I take average of function. When my function take discrete values and return discrete values. But how about the continuous function? How do we define an average? How do we define an average? You must have seen before. But that's very good, right? That's very good. That's very good. So the average, but then, so our friend here, our classmate here say, okay, I'm going to take the integral from AB of our function f x dx, and then AB. That's good. But now I'm going to ask you a question. What's your name? What's your name? No, this. You just came. No, this person. Just answer. What's your name? Say again. Laurent. Oh, you sent me an email, right? Is that right? Laurent. Okay, sorry, I'm not going to say Chinese correctly. I'm trying my best. So Laurent, have you ever asked yourself, that is what I know before. This is certainly I have new. What is the relationship between them? Because that's where you learn, right? Because if you don't connect connections, then you learn two new separate concepts, which have ways of memory. If we make connection, then we just remember only one, and we can derive the others. Right? That's the key in effective learning, at least from my point of views. Especially if you want to become a researcher, right? There's so many things to learn. We have to learn. We have to do a transfer learning way. Why the function defined this way, but the sequence defined the other way? Are they related? Are they the same? Have you ever asked yourself that? By the way, we're going to go to laws of large number which have the similar form, right? I'm not actually talking about for fun here, right? Because I'm trying to lead us to a laws of large numbers. You wanted to say something? Yeah, please. Discrete measure. Yeah. That's one way to think about it. Yes, that's one way to think about it. But actually, let me do a even more elementary way. Okay. Let me actually do a more elementary way now, right? So I'm gonna do actually a very elementary way, right? So let me actually right? Let me chop. I'm gonna chop my interval, right? I'm gonna chop my intervals. Okay, so how is it related, right? So let me actually, another question that I'm going to ask ourselves question, how is it related to the S bar above? Now we're going to use the S bar, we're going to use elementary definition to derive this, okay? Then we convince ourselves, right? We're going to convince ourselves this is not something foreign to us. It's actually that. I'm going to try to convince ourselves on that, okay? All right, so let me actually chop our interval A, B. And for the sake of simplicity, right, I'm going to chop into the uniform. It doesn't matter. We don't need to do a uniform. And I'm going to tell you why in a second, right? So I'm going to do, this is, S1 S2, or maybe to do something different. So X1, X2, dot to Xn. Okay, so of course, right? This we can form a sequence of xi, fxi here, right? I from 1 to n. Of course, right? The average of f would be summation. If we use the elementary definitions of average, at least we can do this. Well, at least we can do this. Okay, so we just use the standard average definitions. Okay, now notice that, right? If I define delta x, actually I'm gonna do. I think it's okay. I think it's okay. Let me actually do this by everybody. I'm gonna do x plus 1. Okay, where n plus 1 interval. Just make things a little bit nicer. Okay, it doesn't matter. You will see it does not matter. I'm sorry. Take it back. I take it back. N. I'm sorry. I take it back. My apologies. My apologies. Okay. All right. So when you see that delta x, right? Delta x is b minus a over n minus 1. Right. So we have, because we have n values, so we have n interval, n minus 1 interval, and each interval is b minus b minus a, right? Times b minus a divided by n minus n minus 1. Okay, so so we have n minus 1 interval. So if we want we can actually change thing a little bit, right? We're gonna change thing a little bit now. We're gonna replace this with b, because n, right? So n I'm gonna replace that. I'm gonna multiply by n minus 1 over n here, and then I'm gonna do 1 over n minus 1, and then summation of f xi, I from 1 to n. I haven't done anything special yet, right? We haven't done anything special yet. We have not do anything special yet, but then this is n minus 1 n here, and this is nothing more than delta x, right? Summations of f of xi delta x, I from 1 to n. Yeah. Yeah, actually I have to do 1 over n of b minus a here as well. Good. Yeah, so we it actually at the end of the day does not really matter here, right? But you want this is I from 1 to n plus 1 or n minus 1? N minus 1, yes. Yeah, that's right. So actually, that's what I originally wanted as well. But I just want to make things a little bit easier. But I agree with you. I thought I should have done n minus 1. It's actually look easier, right? Actually, which would would make actually easier. Okay, so actually follow our classmate suggestion. Okay, let me change a little bit. Okay, I think it's just make our life a little bit easier. Okay, everybody. So give me 1 second. Give me 1 second. Let me actually do this so that you can see very clear what it is. Okay. So I'm sorry. Okay. So my apologize. Let me actually make things a little bit cleaner. This is what we do here. Actually, is also correct. That does not matter, but it's a little bit less clean. Okay. So I'm still do. I'm gonna still do x1 on the way to xn plus 1. I'm gonna do this. I'm gonna do. You see that? Remember that I'm a little bit hesitating to see whether I'm gonna do n plus 1 or n. Then I'm gonna do this is c1, okay, and then c2, dot to cn. Okay, so this is now much better. I from 1 to n. Okay, good. So I chop my interval a b into n interval instead. So I have n plus 1 points, right? But I have n exactly n middle points, right? Of an each, right, is actually at the middle of each interval. Okay, now actually everything should be very, very clear. I should have done this, right? But I'm a little bit lazy, but I think that lazy was not good. Okay, so let us redo it a little bit. This is much cleaner. This is much cleaner. Okay, so therefore the delta x is equal to, in fact, b minus a over n. So exactly b minus a over n, right? Because we have n subinterval. Everybody okay with that? Right? So I'm going to take the average of f because I know f at these n points, right? I have n point total. So I'm going to take the average of f at usuals. And now I'm going to replace, right? I'm going to use the definition of delta x there. I'm going to sneak in delta x by divide and multiply by 1 over b minus a, right? So then I have fci delta x I from 1 to n. So this is actually much cleaner. But of course, now we have to, there's a trade-off, right? But we have to use 2 sequence instead of x and c. Okay, now, right? See, as soon as I write this, and because the reason is that you are most of you are mathematics student, right? As soon as I write this, right, you immediately, this is a Riemann sum. See that? A special Riemann sum. And notice, right? Ci does not need to be in the middle. And second, delta x does not be the uniform. Okay, but we should make it for simplified derivation here, right? So as soon as you see this, say, oh, this is actually Riemann integral or Riemann sum. If I take n go to infinity, or I take, in other words, right, the partition size, delta t go to 0, this become an integral. Everybody see that? So if I take in the limit, when delta x go to 0, right? Or in this case, it's equivalently to n go to infinity, because we assume that on the interval the same, right? Then this is nothing more than 1 over b minus a integral from a to b of x dx, right? And using Riemann sum here, right? Riemann integral. If you learn Riemann integral before, right? Otherwise, think about this, everybody. Thinking about this. Actually, you don't even need to know a Riemann integral, right? This is nothing more than the area under the curve, right? So if this is just even, high school student can do this. This is x, f, right, x. If I have our interval from a to b, if I want to calculate the area of x under the curve, right? What I do is just a chop. You see that we chop this into small pieces. And you see that this is I here, right? And then this is f of ci. So we actually approximate, right? Each area here by a rectangular, right? We approximate, this is nothing more than the area of this, right? rectangular. I sum up on the area, right? And when our partition or our interval go to 0, right? Then the sum of all the area is exactly the area under the curve. This is what we learn. Our intuition in high school. This is area under the curve, which is exactly this, or rectangular rule, if you're thinking about that, right? So you can think about Riemann sum, or you think about area. If you say, oh, I don't know Riemann sum, then look at that figure, right? On the rectangular sum, rectangular rule. So what I have shown you, right? I have shown you, what I have shown you sound like we silly, right? We take 20 minutes or so trying to make connection between the standard sum that we learn in elementary school, right? With like more high school type of average, right? This is elementary average, right? This is high school or college type average of function. They are related. In fact, right, this is actually a direct consequence of what we learned from elementary school. And I mean, for me, this is actually kind of beautiful, right, to see. Okay, so now actually I'm gonna do one more step, right? Then we see, right, that therefore this, right, if, right, that this is actually on the other hand, this formula, but, let's say but. Now we actually go to expectation, but if M is a uniform random variables, right? Then we know, remember, then we know that the density of M is 1 over B minus A, right? Remember that with respect to the Lebesgue measure. And therefore, the expectations of M is equal to the integral of M pi of M dm, right? Which is equal to the integral of M over B minus A dm, which is equal to 1 over B minus A M dm. Oh, you see that, right? You see that this is, it doesn't matter, right? I can turn this to x dx, doesn't matter, right? So you see that, right? You see that when f is actually equal to x, when f equal to x, it is expectations. It is expectation, right? So we show that we see that this is nothing more than expectation, right? This is nothing more than thinking about f, right? Thinking about fx is equal to x or fm equal to m. This is nothing more than the expectations of f of x, right? Or f of m, right? So, and it's actually an average. And this is actually another way to think about why the expectation is average. Everybody remember that when I introduce you expectation, right? We call it average, right? And in fact, you see that we actually have shown that the expectation and average is actually the same, at least for uniform random variables. Everybody see that? The expectations, right, of a uniform random variable, right, is nothing more than an average. The usual average, elementary average that we learn, right? So that's why it's called average as well. Okay. All right. So therefore the question that we're gonna ask ourselves. So far, right? We limit ourselves. Think about this. In other words, right? In other words, actually, let's say here, right? Let actually we make a conclusion, right? Therefore, for uniform random variables, we can approximate the expectations of any function of m as, right? We can approximate, or we know that, right? We know that the limit Actually, this is equal to the limit of f of mi, summation of I from 1 to n over n, and go to infinity, right? That's what we just showed. That's what we just showed. We just showed that for random variable, right? Let me go up here a little bit. For uniform random variable, right? You see that? For uniform random variable, this integral, which is expectation, we just show, right? The expectation is equal to the limit of that. We just show, right? Very simple argument, mathematical argument. We don't even need probability to conclude that, right? To conclude this. We don't need probability to conclude this at all, right? So, so the expectation of any function by simply take the average and take the limit, and we know converge, right? Of course, the converge in which sense, right? That actually important that we need to address in a second. But at least forget about the rigor there, right? We know that this standard average gonna converge to the integral, right, or to the expectations of any functions. So which is nice, which is nice. Now the question that we're gonna ask: how about if, right, the interval is not bounded? So far we do the derivation that we do, right? Is that the integral is bounded too? What if, right? What if m is not uniform, right? In particular, right? In particular, the question that we're gonna ask is that is this is still, right? Is this formula that we just show, at least for the uniform random variable on the bounded integral, E star, right, or does star formula does. In particular, the question that we ask is that does star still hold? Does it still hold? And that's the beauty, right? That's the beauty of a laws of large numbers. Actually, the laws of large numbers say that it still holds. Okay, so that's the beauty. But before we go to that, to answer this question, we need to introduce a couple of things, right? We introduce a couple of things. The answer is A, yes, by the laws of large numbers. So the laws of large number is not something foreign to us, okay? So that's what I'm trying to show you so far. All right, so we need to do some definitions. Definitions to actually make things a little bit more rigor, right? IID, or independent identically and identically distributed. So we're going to look at the IID random variables, okay? So that's what I mean. So identically, okay, I'm sorry. Yeah, independently and identically distributed. Okay, the definition is the following. It's very easy. MI, MIR, IID, draw from up from a probability measures mu m if mi as a random variables, as a random variable is distributed. Distributed or governed, right, by mu m. Okay, so we do a very loosely definition here, right? But so basically, we have a whole bunch of random variable. They have the same law. They governed by a same, right? They governed by the same probability distributions. Okay, so we're gonna loosely define IID that way. All right, so then we need one more definition before we go to the laws of large numbers. Almost surely conversions. Almost surely conversion. Almost surely conversions. Okay, so a sequence of random variables, a sequence of random variables, random RVS, a sequence of random variables, MI. So I put omega there. Remember that the random variable map from a sample space to a state space, right? So a sequence of random variables have sequence of functions, right? So if I know that some undergrad student here and all, some even student that you haven't looked at your sequence of functions, right? For the sake of understanding, it's just, a sequence of numbers. Think about this, right? For each omega, this is a sequence of numbers we know from high school, right? High school, if for each value of omega, this is a sequence of numbers. So we have many sequence of numbers, right? And that is the infinite. Actually, we have infinite sequence of numbers. That's called sequence of function. But other than that, don't worry, right? Just for each omega, it is a sequence of numbers. Okay. So we have a sequence of random variables. Converges almost surely. So typically we do AS, right? AS. Almost surely to a random variable M omega if the following is true. If the following is true, you take M, you take the N, right? You take the N random variable because you know that N, right? N can be anything between 1 and infinity, right? We take the N random variables, you evaluate at omega, and we check to see whether it's different than capital M omega. So you see that? I write very slowly. I take the nth random variable in that sequence. I evaluate it as omega, right? Remember, that's a function, right? So I evaluate my nth functions at omega. And I evaluate m, which is another function, right, at omega. And I check to see whether they are different or not, right? I want to check the different or not. And I not only I check the different or not, but I'm interested in the limit. I'm interested in the limit when n goes to infinity, whether they are different or not. Okay? Okay, and then I set up omega. The set of all omega such that the limit, right, is different than m. The set of all omega such that the limit functions, the limits of my mn, right, at omega is different than my target functions. I collect all of that omega. Everybody see that? I collect all of them and put them a set. Each of them have this property, that is the limit of mn omega is different than m. Okay, I collect all of them. And I'm gonna measure the probability of that set. Okay, I measure that probability, that set. And if that probability that set equal to 0, if the probability that set equal to 0, then we say that our sequence of random variable converge almost surely to this M, right? So basically, you think about this, right? The probability that my sequence is different than this is 0, right? Then that is a almost surely conversion. But if you take integration before, right? Riemann integration, especially Lebesgue integration, this is the same notion of converge what? Converge what? This is just a probability language. Almost what? Almost everywhere, right? This is a probability way of saying almost everywhere, right? This is nothing more than converges almost everywhere, right? That is the set that this sequence does not converge have measure 0. See that? That measure 0. The only what they measure is that this is the probability measures, right? So when the probabilities people, right, when they do this, right, they just cast into a actually more intuitive, right? Almost surely that we converge. Almost everywhere sounds like very mathematical, right? But almost surely. So that means with probability 1, okay? Actually, let me turn it into probability 1, okay? Then this actually may be even easier, right? Or equivalently, right? If I take the sequence, I evaluate M, right? Actually, I take the limit. Actually, the correct way to write it is I'm gonna take the limit. And if that limit is equal to M omega, and I collect on omega such that is true, I collect on the omega such that the limit of my sequence is equal to my functions. And I'm gonna measure that, right, probability of that set, it will be equal to 1. Right? So that's why almost surely conversion and conversion with probability 1 is the same. Okay? So so then let me actually write out in terms of words here. So this is to say that is the set, right? That is the set of omega on which the limit of our sequence that is different than our target function has 0 probability. Measures, right? Or our sequence M omega I from 1 to converge to M, right? With probability 1, with one, right? So we typically write, right? We write M I or M N omega converge to M omega AS almost surely. Okay, so that's the notion of almost surely conversions. Now we are ready. Now we are ready to talk about laws of large numbers. Theorem. So we can prove, but I think that there's actually, in my lecture notes, I show you a simple proof, right? Simple proofs. We don't need backward martingale, but the most beautiful proof is actually backward martingale, right? But the proof that I gave you in the lecture notes is very simple, right? Very simple, but it's require extra assumptions. Of course, there's no free lunch. If you want simple proof, you need to assume a lot. Actually, we assume that the fourth moments of the random variable is actually finite, right? You don't need fourth order or fourth moment to be finite in order to prove the laws of large numbers. But if you want to have a very elementary, easy proof, which is, look at my lecture notes. We're not going to go through because we don't have time. Let's time we come back. But we need to go to the stochastic gradient descent first and prove that. Okay, so let's do a theorem here. Assume that mi are IID from pi m, right? That means from a probability measure with density pi m with respect to Lebesgue measures. And then we assume that we assume two first. Second, we assume that the mean or the average of m is finite. Third, we assume that the variance, which is sigma square, by definition defined as the expectations, the expectation of m minus m bar and square. So this is called the variance, right? So the expectation of the mean square, or this is the mean square error, right? Think about the mean square distance between our m with the mean, right? But other than that, it's just the terminology variance, right? But it's a very meaningful definition there. So we only need second moments to be finite. That's enough. But in the proof, I also require the fourth moments in order to make things easy. Okay, then. So we only require that the first two moments to be finite. Then, if you take the sum of I from 1 to n, and you take the average, right? You see that? Our beautiful elementary average. And if you take the limit and go to infinity, okay, so then this converges almost surely to the expectations of m. Okay, so or if you want to write this is just the integral of m pi m dm, which is a special case, right, where we know the probability density. You see that we don't even need to know the probability density, right? Because this generic, it say that expectation, and you see that we don't even need this. All we need is that these are IID random variables, whose average or the first moment, right? The first moment and the second moment is actually finite. All we need, right, is we can cover this. Then we know that the usual average that we know from elementary school, right, converges to the mean almost surely. Okay, so that is our and then I talk more about this in the lecture note, right? More about other things as well. So why do we need the laws of large numbers? Right? Why do we need laws of large number in machine learning? In fact, that's a key. And in the next hours, right, we're going to have 10 minutes break, and then we actually go back to our machine learning again, right? We're going to look at risk minimization formulation again. You see that? You see here? Actually, before we go to the break, I think we have still 1 more minute. You see that this is the original risk or the optimization function, right? Remember that we want our function in the class as close as possible to G, which is unknown functions, right? On average, or over the whole domain. And remember that I said, oh, but we don't know a G, right? We don't know G, but lucky in practice, we observe G over a number of samples. So we're gonna replace that integral with this. Remember, I asked you why should I put one, and first, y sum, right? Second, y average. Now we know. The large of large number tell us this actually converges to that almost surely, right? So we didn't actually introduce this, unjustified, right? Now we justify why we need this because we know this is going to converge by the large of large numbers. So then therefore it's legit, or it's good for us to actually now to investigate this, right? We're going to investigate it because this, we know this is a good approximation of that, as long as n is large enough, right? Okay, now so we next we're going to try to solve this optimization problem using stochastic gradient descent. Given the fact that we know this is a good approximation with that, thanks to the large of large numbers, and now we know these are random, right? Random IID. By the way, this must be an IID, right? Identically, independently distributed from the sum distribution. Then this converge, right? So we know that these are IID random realizations. Let's see how we're going to talk about gradient descent. Why does it converge? Converge in which sense? In the last hour. Okay, so let's have a 10 minutes break, and then I see you in. So let us now do the stochastic gradient descent, but let us review what we have. Not review, but let me actually post some notations. Okay, so we call S as a training set. S, some notations that we're gonna put down. As our training set is we're gonna take X, I, Y, I from 1 to N. So we have N of them. And we assume, right? We assume, and then we call ZI is equal to XI, YI. And it is distributed some distributions that we don't know, right? So we don't know this. This is important. This is amazing of machine learning, right? Because we don't need to even know, because if we know, things become much easier, right? It's unknown distributions. All we know is that the samples, so we have N samples from that unknown distributions. We don't know, right? We don't know the true function either. Don't know the true functions. G. Okay, so we don't know that either. So the true function, remember that the true function take us from X to Y, right? And we assume that of course YI is equal to G of XI. But other than that, we don't know anything about G, right? And sometimes we also, right? We also call F star as G to make it really distinguished, right? Start. So the key that we know, right? So we know that we don't know. Let me actually remind us here. We don't know F star, and we don't know D either. Okay, so we're gonna define the risk. So definitions. We're gonna define the risk. RH as a risk, right? As a risk with associated with the learner. I'm gonna divide RH as a risk associated with a learner. Okay, so learner. So a learner H, where H is a function from some some space, right? And typically we call it this is the hypothesis space. Hypothesis space. So let's actually give an example, right? So example to make sure that we know what it is, right? So the risk function, for example, the risk example, reach H is equal to expectations of F of X, or I'm sorry, H of X minus F star, which is the true square. For example, right? This is the standard mean square error. So for example, this is a risk, one of the popular risk, or L2 risk. This is an average error between the unknowns. This is a learner, right? We call it a learner, and this is F. Well, and for example, the first is this, second is this H is based of neural network, right? Neural network functions. From parametric, right? Deep neural network, DNN. So the sets, this is a set of function from DNN that we looked before, right? A few days ago, we spent a lot of time on deep neural network. And for each, remember, for each way and biases, right, we have one functions. So H is just one of them. And we call it a learner, right? That's a language of machine learning is called a learner. Okay, so that's what we have so far. So we also define a loss function, by the way, right? We also a definition here, another definition that that we're going to use in our is L is called the loss functions. L as a function of X of H and Z and the true. Okay, so but typically we just write, right? We just typically write to make simplify. We're gonna loss function H Z. It's a loss function, lot functions. Right, and typically the loss function and the risk is related. The risk is equal to the expectations of the loss function HG's over on Z expectations, right? So basically the expected loss, right? For let me actually basically give you an example so that you know what loss function is. So let's say the classification problem, right? So let's look at the binary loss. So binary. Let's look at the binary problem where yi can be either 0 and 1, like two classes. We need to classify that two classes. Then the loss functions is typically written as h of z is equal to 1. 1 of if y is equal to or h y is equal to the loss function is not h, right? So this is a very interesting indicator function, right? This is indicator function. So this is the indicator function means it is equal to 1, right? It's equal to 1 if y x is equal to h of x, right? And if it's other than that equal to 0, y of x is different. Of course, you see, right? If they are the I'm sorry. That's wrong. This. Let me turn this off. So it is equal to 1. Let me repeat that. If this different, if 0, if they're the same. Oh, gee. See F star. Let me make sure. Now F star here. Sorry, so it's actually very intuitive. This is the loss, very popular loss function for classifications. The loss is equal to 1. That means you incur a loss if you are not doing correct, right? If you classify things correctly, that means this must be the same, right? If you are different, then you incur a loss, $1. Think about that way, right? If you're doing correctly, there's no loss, right? If you classify correctly, there's no loss. So that's the definition of the loss functions for. Remember, z is the combination of x and y, right? Or x and f. Remember, y is equal to f star. So that's why originally I put y there, but I put y and f star is y. Remember, y are. Let me go back here a little bit to make sure that you see, right? Y are instances, right, of f, right? Y are as instances of f. Okay. Then actually for the regression problem, let me actually do also regression problem. And this is by no means unique, right? The regression problem. Then the loss function, there are many loss function, right? In particular, like for the loss of h, z, in this case is equal to, y, g, I'm sorry. So this is L1 loss in f star x minus h x. This is L1 loss. L2 loss is equal to f of x, f star x, minus of h x squared. This is L2 loss. See L1 loss. This is L2 loss. So these are, two perhaps most popular loss functions. Okay. Okay. So our task are definitions of the they also call generalization error. Generalization error. And this is where, in machine learning or deep learning, we call generalization, right? Whether our method generalized or not is when you take a method generalized or not is when we look at the generalization error. And a generalization error is nothing more than actually our risk there, right? Is equal to expectations of this is a different name for the risk of log functions hz. Okay, so that's a generalization error. Of course, we want the generalization error to be small, and unfortunately, right, the risk or generalization error we don't know. We don't know because we don't know two things, right? We don't know f star, we don't know the distributions. So typically we have to do a empirical risk. Or empirical error, right? Generalization error. And empirical risk is by, okay, this is by the laws of large numbers, by, laws of large number. LLN, laws of large number, everybody. LLN, law of large numbers. We define empirical risk. Empirical risk is equal to 1 and loss of h of x I, right? And we put z there, but we can also do f star xi or yi, maybe to do very clear. Okay, the sum, of course, summation I from 1 to n. So by the laws of large number, typically we approximate the generalization error. So we want to minimize this, but in practice we cannot. We're going to minimize the surrogate, right, or the empirical version of that. In a more, we do this more in abstract form right now. Okay, so and of course we have one more definitions. Remember that H is in our hypothesis space, right? And the hypothesis space typically we parameterize by weight and biases by W. See, weights and biases together. We combine all of them into big vectors, W. We don't, I mean, I'm lazy to put W with vector here, right? For in general vectors, but to avoid cumbersome notation, we're gonna forget about the arrow size. We understand that this is vectors, right? Of all weight and biases. Then the definitions, the optimization, the minimization of W's of the risk N, right? And H is in turn, the risk is a function of W vr H, right? Remember that H is a function of W. So this is the empirical risk minimization problem. So this is known as the empirical risk minimization problem, empirical risk minimization problem. Some notations. Okay, all right. So we're gonna do a couple of one more notation to make our life a little bit easier. Okay, one more easy in terms of writing. Okay, and then we done. So we make things a little bit symbols by we're gonna define. We're gonna define F omega as 1 over n. Actually, let me see, make sure that I'm gonna the F of omega. I'm gonna define what this our risk of n here, just to go back to our usual notation. Okay, F. Instead risk, of course, right? The stochastic gradient that sent I'm gonna show you actually generic for any F. Of course, risk, right, is one of them. But instead do Rn again, right? We just do F omega, and every omega is Rn, the risk. Okay. All right. So we need to do a few assumptions. So assumptions, key assumptions. And we're gonna make our life very easy, right? By make the seamless assumption to make our proof to go through easily. And of course, right, you can looking for more advanced proof with less conditions or milder conditions. But we're gonna do the easiest one. We assume that, right? We assume that the risk, it's we assume that the log functions. The log functions. Remember that the logs functions is in terms of H, and this is function of omega, right? This is convex in omega, right? And therefore, we assume basically indirectly F omega is convex in omega. That's convex, right? And we also assume that F is differentiable. We don't need to, right? All we need is actually, we don't need differentiable in the proof. We only need the convex. We can use the more generic notion of gradient. We actually don't need gradient. In fact, we can do subgradient, okay? Subgradient is actually much more general notion of gradients. And the proof actually go through with subgradient as well. But we're gonna make things easies, right? By just say that f is a differentiable and convex. And remember, right? Remember that these two together, remember that we learned last time. We learned last time that this is equivalent to saying that f of w minus f of w prime is less than or equal, or less than or equal to, let me see, less than or equal to the gradient f at w, and this is w minus w prime. Okay, that's the inner product. Actually, we do this. Let's do this. Transpose of w minus w prime. Right? Remember, that's if and only if f is convex and f is differentiable, then we have this. If and only if. And we're gonna actually write interchangeably. We also write this, the inner product, as the gradient of f w times w inner product, right? Okay, we also write this. Okay, so that's convexity assumptions. We are do one more assumption. Another key assumption is that the gradient of f, okay, we assume that actually less than or equal to L, right? L is less than infinity. In fact, assume that Lipschitz, assume that f is Lipschitz with Lipschitz constant is enough. Is sufficient. But we make it a little bit easier for we assume that the gradient of f, not only the function is differentiable, but it's also have a bounded gradient. Okay. Okay, then actually we actually in the position to state our gradient descent. Okay, the gradient descent algorithm look like this: SGD, gradient descent, stochastic gradient descent. And SGD is the popular name or acronym for stochastic gradient descent. Okay, what do we what are we given? The input of the stochastic gradient descent are W. We start with W1 in Rn. Right? We start with some initial guess and positive sequence eta. This is actually, I'm going to change notation a little bit. Okay, I'm just I'm going to follow and let you know, but this is actually delta that we learned before. Delta, remember that the gradient descent we had delta, but now I'm going to do eta, and S is greater than 1. Okay, S is greater than 1, and the IID. Okay, IID, random variables or random sample, random variables Z1 dot. So we assume that we have K sample. Remember that these are from the training set, right? From the training set, and we assume that K of them, right? Each of them are IID draw from a distribution D. Remember the distribution D up here that we don't know, D, right? D that we don't know, and we assume that they are IID for the large number and to be meaningful. But you're gonna see more in a second. Then the gradient descent loop is this: for S is equal from 1 dot to K minus 1. We do what? We do this. We update. First. We take the gradient. We take the gradient as the S step is equal to the gradient of f. The gradient of f. No, not gradient of f. So sorry. Notice that, right? Okay, let me go back here a little bit. there's a loss function up here, okay? So you see that we have a loss function here. Okay, so we have the loss function here, right? We have a loss function here, and then we have an empirical risk here, right? And F is the empirical risk, and we're gonna look at the gradient of the loss functions. Okay, so we're gonna take the gradient of the loss functions. Okay, we assume that the gradient of loss functions. So the gradient of the loss functions. Remember, the loss function depends on h, and it is in turn gs is equal to the gradient of the loss functions hws, and then we draw a new symbol gs. Okay, so our gradient descent look exactly what we did before. So ws plus 1 is equal to ws. So s is now at this moment is given, right? S plus 1 is we don't know. And eta s gs. Okay, eta s gs. So we pick a random. So this is not random at this moment. At this S iteration, ws already computed, right? So ws is given. H is the learner, which we know as a function of ws. What we draw is gs. We pick one of gs here, okay? And they are random. IID, they are IID from the same distributions. So this is gradient descent, right? The only stochasticity is from this. The z is a random variables, right? Random raws from the distributions. And that's it. You just do that. Do again, come back and draw a new one and update. So very stochastic, right? Each time we draw a new random variable and then we evaluate the gradient of the loss functions. And then W bar is equal to, we define, right? We output, actually this is output. Oh, this is important step. This is our output. Output of our gradient descent is W bar. W bar is equal to 1 over K of summations of WS S from 1 to K. So we run K iteration. We take the average, or we either output that, or we output W0 equal to F of W, and we take the minimum. We take the minimum over on W1 dot to WK, right? So we either output this, but typically this is what we want, right? This is typically the output of a stochastic gradient descent. It's interesting, right? Unlike the gradient descent that we did before, the output of a stochastic gradient descent is the average of all previous step, all of the iteration that you do. Average of all the iteration that we did. Okay, that's what we assume. Okay. I think I do one thing that is not correct. Okay. I do one thing that is not correct, by the way. I'm sorry. Okay, let me I'm gonna make sure. Let me make sure that everything is good. Make sure that the yeah. Okay. So now actually a theorem. That is now a theorem, right? That is stochastic gradient descent iterations. So the theorem is the following. The theorem is following. Okay, let LWZ be convex. Be convex, like we assumed before. Be convex, almost surely with respect. Oh, you see that almost surely again with respect to W, of course. And and when you take the gradient, right? We can take the GS, which you remember that the gradient. I'm sorry, I think I put a wrong assumption there. GS is the gradient of the log functions, right? Not F. The gradient of the log functions at any point, the GS here, and if you take the expectations with respect to G of W, right? Okay, I'm sorry. Let me actually do so the second moment of the gradient, that's what we assume, right? Is actually less than or equal to L squared, right? For all W, where remember that GS is equal to the gradient of the log functions at H W Z. Okay, so if you take the expectation with respect to Z square for GS, okay, we assume that it is finite. Okay, so then the following holds. Then the following holds. If you take a constant, so it's actually NS eta S is equal to R divided by L square root of K, where the R where expectations. Okay, this is from Z1 dot 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 to ZK of W of W1 minus W star square. The expectation of this is less than or equal to R. Okay, so basically we assume, right? We assume that the first step of gradient ascent. Okay, you pick, and of course W star is the truth, right? W star is the truth. Where that's what I assume. Where and W star is the unknown truth. Okay, so we assume that we take a fixed step, right, in the sense step. So remember that we run a K iteration, and the step is R over L square root of K. L is this from here. R, this is the initial step that we take, right? The initial step that we, initial guess. We basically say that the initial guess is not that far from the star in the sense that it's on average, right? We assume that if we take the expectations over on the Z, if we take the expectation over on the Z, right? If it's ever actually depend on Z, which typically this is actually not, right? These are actually not. So remember that the expectation of something that is independent to the variables, right? Remember that expectation that we define. We remember that we take expectations of any function, right? Is equal to the integral of f of let me actually remind you here so that you don't feel confused. I'm going to erase this in 1 second, okay? F of m. Let me actually let's say that we have a probability density. It doesn't matter. It doesn't need to be that density, right? This is expectation. If I replace this by 1, right? This become 1, right? And this is, of course, this is mu of m dm to be generic, and this is over the whole state space, and we know this is equal to 1, right? Basically, if you take expectation of something that actually does not depend on the random variable, you don't do anything. You get 1, right? So if this, typically this is does not depend on Z at all, right? Because this Z is random draw, this is the way. So this expectation doesn't mean anything. It basically say that W1 minus W star square less than or equal to R square. Everybody see that? You get it? Right, so if this function does not depend on m in particular, right? In particular, let's say expectation of anything that does not depend on m, then FW here Then we get to add up W, because W does not depend on M, right? This is mu M dm. This is 1. Oh, F W's. So it does not matter. Okay? Time 1 here. So it does not matter. And about battery, I think. Yeah, we don't have any battery left. Okay, I think it's okay. We don't have battery. Okay, so yeah. How this one work? Oh yeah, this is M. Good. Okay, so let us back to this. Actually, microphone is better. I can talk a little bit about less. Okay, so this is also we assume, right? We assume that the gradient of the log function, where is it here? The gradient of log function, the second moment of that is actually finite, right? So everything is good. So proof. So let us do the proof now. The proof is actually very similar to gradient descent. Yes. Hmm? Sorry, I don't understand your question. What is it? Asking whether this line in the purple. Oh, okay. No, that's it. That's if, right? If then. I'm sorry. That's a. Oh yeah. This is the step side that we pick. If you pick the step side this way, and if you assume that the initials gets is r distant away from w, then this holds, right? That means on average, you converge to the truth. Okay, so we look at a seamless version of the stochastic gradient descent, and the proof is actually, like I said, right? It's not going to be not that difficult. We use exactly like we did this before. Okay, so because L, right? L is Lipschitz. So actually, I'm going to ask you to do this, right? I'm going to ask you to do this if we have times. So we see that the gradients we have since GS is equal to gradient of F of L H W Z, right? That is our G. Then since we have the gradient of F is equal to, in fact, the expectation of G with respect to Z. Okay, or this is expectations of gradient of L H W Z. Okay, so remember, right? Remember, F is a so this is. So I'm going to put a question mark here, ask the homework, or if we have time, we come back. Okay, so this is the step that we're going to skip. So remember, that's the F, right? F is actually the expectations. The risk is expectation of the loss, right? And F is actually the risk. So that is actually quite obvious by the definition of the risk and the loss. Okay. So let's look at, well, please take a look at that. It's actually trivial, but I really want you to see. And by convexity and differentiability, right, by convexity of L with respect to WRT, with respect to W, we have that, but before definition of F, right? F of W S. If I want to compare the distance between any step FWS and our W star, FW star. Oh no, ran out of battery. Actually, we need to actually, Chung Hao, can you actually ask? I think we need a different one because I think mine is actually ran out of battery very soon. Yeah, 10%. Well, I think hopefully we can have enough. Let me try to. I cannot see very clear now, but it's okay. Let's try. Okay. So the F, right? FW. Actually, let me do this so that you can see a little bit better. So L of W Z S minus L of W star Z. Right? By convexity that we start. By convexity. So this is less than or equal to the gradients of L, right? The gradient of L at WS times WS minus W star by convexity, right? By convexity of L. Okay, let's remember that we proved that even only if, that way I just mentioned before. So then take expectation both sides, right? Take expectations both sides. And notice that F, right? Our F W is nothing more than expectation by definition, expectation of L of W Z with respect to Z. Then we have F of WS minus F of W star, which is our risk, right? This is 1 point, only 1 point. And this is the expectations of gradient of L WS Z, Z here. Inner product of WS minus W star. And you see, everybody, we take expectation both sides, right? Remember that expectation is an integral, right? So this is the inner product. So this is inner product of two functions, right? Let me actually put Z in here so that we make sure that we understand things a little bit better. Remember that the log functions is a function of Z. The log function is a function of the training, right? This is not a training things. So when you take expectation on both sides, this is, you think about expectation is integral, right? Integral. And then the inner product itself, this is inner product itself. The inner product itself is a linear operator, right? So the integral of the sum, think about the integral of the sum here, is nothing more than you can take the expectation of the integral with respect to Z alone, right? Because this is just the sum of each component of Li and WIS, WI star here, sum, right? So the expectations only with respect to Z, right? So you can put the expectation inside of the inner product or the sum here because of linearity of the integral, okay? So we're not gonna go through that detail because that hopefully is obvious for you. Okay, then we actually now can continue. Of course, this is actually our GS here, right? Our definition. This is G of S here, right? G of S here. So that's this expectation of GS. But GS by stochastic gradient descent. Let's go up here in the iterations. Where is that? So GS is equal to WS plus 1, right? Minus WS, or WS minus WS minus plus 1 divided by the eta S, right? So we're gonna substitute GS is equal to WS minus WS plus 1 over 2 eta S. So we're gonna do substitution in there. Okay, so we're gonna do a substitution in there. Then what we have is this. If we do up substitution, you immediately get this is expectations of WS minus WS plus 1 over eta S. Okay, and that, of course, right? Of course, multiply by WS minus W star. Okay. Okay, so we continue. We're gonna continue. We're gonna continue. I'm gonna do a trick. You see that we have WS minus WS plus 1, WS minus W star here. The expectation, you remember that I can take in and out. That doesn't matter. I put it in. I'm gonna put it out again. This is equal to. This is equal to. So we're gonna take out a couple of things. And remember that eta S is equal to eta, right? Is equal to R L square root of K. Does not depend on anything, right? And it's a fixed thing. So I'm gonna take it out, and I'm gonna take it out at eta. So I'm gonna take it out as 1 over eta, 1 over eta. Then I have expectations of two things: WS minus WS plus 1 in the product with WS minus W star. Okay. Okay, so that's so far so good. And now I'm gonna do a trick, subtract, like we did last time, right? Like we did last time with the gradient descent. I'm gonna do a trick, and then we sum thing up. We're gonna cancel thing out, okay? So what I'm gonna do is I'm gonna do a trick. I'm gonna insert WS plus 1 here to have this similar thing, right? So WS WS plus 1 here. I have WS here. I'm going to add and subtract WS plus 1, like we, did almost like we did last time. Okay. So we gonna do that. So this is actually on the other side. I'm on the other side. I'm sorry. I think I should. Let's see. Yeah, I'm actually, this is on the other side. Okay, so I'm gonna expectations of. I'm sorry. I'm doing on this side instead. So WS minus W star plus W star minus, because W star is something fixed, right? I'm sorry. I missay what I just meant. Because W star is fixed, we're gonna break. These are changing. These are changing, right? Both of them are changing. So we're gonna break into something changing, something fixed, and we combine with this one. Okay, so if I do that, if I do this, right, and I multiply them out, okay, I multiply them out and complete in square, okay, I let you do that, right, expand them out, or distribution of property. Sorry, I think we a little bit fast here, but these are elementary operation, everybody, right? We already did something similar. Distribution of property plus complete in square, like we did last times. Okay, so if I do that, then you can rewrite this as 1/2 of eta. So it's split in square. You take the 2 outside. What you get inside is this. W, you get two things. So why don't we actually see this? Not sure I make any mistake here. Give me 1 second. Did I make any mistake here? Oh yeah. It will, after you do complete in square, you have WS minus WS plus 1 square, and then plus WS minus W star, and you expand them out, and then you complete in square, you get this. Okay, so please finish that things. Very nice, right? Like we did last time when we complete in square, we can get back to this, which is very nice. Square things, and then notice, right? So we're going to apply again. We're going to do again. Remember that WS minus WS plus 1 is equal to negative, right? Eta S GS, right? Greater than cent, right? Oh no, plus. Greater than cent. Okay, so if we apply the greater than cent formula definitions, then we have expectations. The expectations with, this is our G eta S square, right? So we have eta G square plus expectations. And of course, this is our expectation. Let me actually go up here. Want to make sure that we do correctly, okay? So this is GS, the expectation with respect to the S, by the S step. Remember, actually, let me go back up to the greater than cent here. The greater than cent, every step we draw, right? Every step that we draw is GS, right? And GS is one of these, which is random variables, right? So I have to put GS there to make sure that we are talking about GS now. To be GS with respect to GS, expectation with respect to GS, the new random variables, GS, and then expectation with GS, and then this is WS minus W star square minus W of ZS, expectation of ZS WS plus 1 minus W star square. Okay, so the expectation is a linear operator, right? So we can do this like I mentioned. Okay, so that is good. And then notice that, of course, right? Of course, now I can take the eta out because eta is fixed, right? So when I take eta out, this we have eta square here, right? And then this is GS, expectation of GS. And remember that expectation of GS by assumptions that our expectation with respect to any Z, in particular here GS, ZS square is less than or equal to L square, right? So then the whole left right hand side there is that then over 1 over 2 eta of eta square L square plus expectation with respect to ZS of WS minus W star square minus the expectation with respect to ZS WS plus 1 minus W star square. Okay, so we conclude, right? Thus F of WS minus of W star is less than or equal to what we just wrote here. The whole right hand side here. I'm going to copy and paste here. Right, because we start with WS minus W. Go up here again. Make sure we start with WS minus W star, and then we use convexity, and then we just do manipulation, elementary manipulations. We get here. So we have to 5 more %. So hopefully it works. So I have to make it very dark in my side now. But let me actually recopy this. Okay. Okay, now what I'm gonna do next? I'm gonna take expectation. Okay, I'm gonna take the expectation with both sides. I'm gonna take the expectation both sides with respect to every. Okay, so I remember that at this moment, WS is already given from the previous current step, right? ZS is a new random variable, right? We draw from the pool of training data, right? But this guy is actually up to this point is given. But if you think about the previous step, right? In the previous steps, each of them is again drawn randomly, right? So now I'm going to take the expectation with everybody. I'm going to take the expectation for both sides. Now take the expectation both sides for with respect to everybody. Now take expectation of with respect to everybody G1, right? Over all step. I'm going to take the expectation to everybody, okay? Over on the K step. Okay? So I'm going to take the expectation over on K step. What I get is this. So I'm going to take expectation both sides. Remember, expectation is integral. Remember that if you think about the integral, then things is a little bit easier. Okay, so if we take the expectations on everybody's right on sides, then of course what I have is the expectation, and then let me actually make it the short notation. Okay, let me make a short notation. Instead of writing Z1 to ZK, I'm just do Z here. Current parenthesis there. I'm going to define Z with the curly at everybody there, right? So to make our writing a little bit easier, then Z here, right? And these are constants. Expectation of constant is itself. We just showed, right, a few minutes ago. The expectation of any constant is itself. Expectations of everybody. So of course, we can do expectation twice. That's fine, right? Remember that I can do expectation of S and then I do expectation of S again. It doesn't hurt anything, right? Because after you integrate out, thinking about that, right? But after you take expectation of S, no more S. This is no more ZS in here. And if I take expectation of S again, it does not hurt anything. I get back, right? Because now this is a constant, a function that is constant with respect to S, ZS, right? Expectation of something that does not depend on your random variable itself. Okay? So it does not hurt for us. It does not hurt for us to actually now just replace on the ZS. He would, of course, if you see that I do double ZS there, but it doesn't matter. Double ZS does not do anything. I can always do extra expectation if I want to, right? As soon as that does not depend on the variables, right? And then I can do extra expectation. So we feel free, right? When we take the expectation over all random variables, then we can just feel free to remove this with Z. Everybody okay with that? I'm sorry, it's a little bit over time. Let me actually give me 5 more minutes. I finish this, okay? Just bear with me on this. We are almost there. We are almost there. Now, actually, finally, I'm gonna do adding some up now, right? Now, the good thing is that now it's allowing me to add, right? Now everything deterministic. Expectation here deterministic. These are number. These are number. No longer random variable. After I take expectation with respect to all random variable, right? I don't have any of course, anybody, if you have to run or have to go, please go. I'm sorry, we turns out that we actually are running late. Okay, so now sum both sides. Like we did in the gradient descent, right? With respect to, right, S from 1 ... to K. Okay, so you see that when we sum, we have a telescope, right? We have telescope summation here. We start with WS, W1 minus W2, and then W2 minus W3, right? And so on and so forth. We see that we're going to cancel out like we did last time in the gradient descent. So same, what we have what we have is that the summations of expectation with respect to Z of F of WS minus F of W star. And remember that W star does not depend on S at all, right? This is S from 1 to K. So if we take the sum, then we have 1 over eta, so we have K, right? So this guy up here, K times, because it's a constant. So K times eta squared L squared. The only one that survive is the expectation of Z of W1 minus W star, right, square. And another one that actually survive is the last guy, right, minus expectation of Z, like we expect, right, W K minus W star. We have exactly the same thing like last time. And of course, because this is a positive, right? This is a positive number. This positive, it doesn't matter. This plus this minus this, of course, less than itself, right? So this is, because we have a minus at the end, so we have this is 1 over 2 eta of K eta square L square plus expectations of Z W1 minus W star square. That's very nice, right? Because we know that this is less than or equal to R square, right? We know that this is actually less than R square because that's the assumption of our theorem here, right? We assume Remember, it's same thing like we did last time for a gradient ascent, right? The first step is fixed. And in particular, we call it R. So this, on the other hand, by assumptions, this is 1 over 2 eta k eta square L square plus R square. Okay. So we have the sum of that, right? Less than this. I'm going to take the average now. I'm going to take the average, both sides. I'm going to take the average, both sides. But divide, actually, let's do instead of average, dividing. Dividing both sides by k. So we have, I'm going to copy down here and you will see it easy. So this one, right? Copy and paste. So we have 1 over k, so I'm going to divide 1 over k both sides, and the right hand side there, right? This is less than or equal to, if I divide 1 over k, so I have 1 over 2 eta k, I'm going to move in here, and then move in there as well. So I distribute, so we have 1/2 of eta L square. Right? Eta L square, 1/2 L square. That's the first term. The second term is 1/2 of eta k R square. Oh, that's actually very nice now. Very nice now. Okay. So eta, you see that, right? What is the best eta? So you see that we're almost there. This is less than this plus this, which is a constant. What is the best eta? Actually, up to this point, we didn't specify what eta yet. We just say that on the step have the same eta, right? We didn't specify what is the best eta. The best eta is the one that make the up about, this is up about, right? To be smallest. What is the value of eta when to make this smallest? What is the famous inequality that we use again to make the right hand side smallest? What did the inequality we use a couple of times before? That has two names. Cauchy-Schwarz, right? So if I do Cauchy-Schwarz, this plus this is greater than equal, right? So Cauchy-Schwarz, this is greater or equal to what? This is a greater than equal to 1/4, right? One. Okay. Actually, here. This is greater than or equal to 1/2, right? 1/2 of square root, or 1/2 AB. 1/2. Okay, so A plus B, right? A plus B is greater than or equal to 1/2 of square root AB, right? AB is 1/2 of eta L square, and then 1/2 of R square eta K. Right? So this is 1/2 of 1/4. Okay, divide by eta. So we have L square R square K. Okay, you see that? The right hand side is always greater than this, equal this by Cauchy-Schwarz. Right? A plus B is greater than 1/2 of square root of AB. I'm sorry, not 1/2, 2. I'm sorry. 2, not square root, 1/2. Even apply Cauchy-Schwarz in the wrong way, right? In other words, this is equal to LR over square root of K. Very nice, right? So, and when does that equality happen? Everybody see that? Let me repeat. This is less than or equal to this sum, right? And by Cauchy-Schwarz, this sum is always greater than or equal to this. I simply pick eta such that this equality holds. What's the eta? What is the eta? When does the Cauchy squat inequality is equal? When A is equal to B, right? When A is equal to B, that means when this equal to this. When this equal to this, you see 1/2 cancel with 1/2. We have eta square here. We have R square. Okay, I'm sorry. The last step, right? Last step, I think we ran out of the battery. But the last step, let us do the whiteboard. Okay. So we have one of K summations of expectation of Z, right? Of F of WS minus F of W star. So that's what we have, right? And then this is less than or equal to 1/2 of eta L square, right? And this is 1/2 of eta K R square. Yeah. And remember by Cauchy squat, this is greater than equal to, right, we already did, right? L R over square root of K. And this equality happens when this equal to this. That means when eta square is equal to R square over L square K, right? That is when eta is equal to R over L square root of K. Okay, when eta is equal to this, then we know that this, right? So then now we after we show that when we simply take eta, and this is the reason why we pick this, right? This is the reason why we pick the step like this. If we pick the step like this, then we have 1K, the summation of expectation with respect to Z of F of WS minus F of W star. Okay, and this is less than or equal to this, right? Because this achieve the minimum. This guy achieve the minimum, basically LR over square root of K. Nice. So we're almost done. We have this. We almost this. Now, we're gonna do interchange. Remember that the integral, right? The integral expectation is integral, right? So we can move in and out with the sum here. This is a finite sum, by the way, S from 1 to K, right? So we're gonna take the expectation out. We're gonna take the expectation out, right? And move 1K in here, 1 over K and sum in here, right? So we have sum 1 over K of F of WS, S from 1 to K. Okay, so when we say this is the sum of F star, the W star, and this does not depend on S. So the sum of F W star, S from 1 to K, we have K of this, right? K of this divided by K is itself. So we still have F of W star less than or equal to LR over square root of K. Okay, we're almost done. Okay, now one more thing. F is convex. Convexity, right? F is convex, right? F is convex. So and by convexity, then remember that by convexity we have what? So we're done with this part, right? I'm gonna erase this part. I'm gonna erase this part. Remember the convexity here, right? F of the summation of 1 over K W S from 1 to K. Convexity, remember the convexity is less than or equal to 1 over K sum over F of WS. S from 1 to K, right? This is the direct consequence of this F of alpha X plus 1 minus alpha Y, right? Less than or equal to alpha Fx plus 1 minus alpha Fy. So this is the direct consequence of this because we just simply take X1. Instead have 2, we have K of W. And alpha is 1 over K, right? As soon as the sum of all the coefficients is equal to 1, which is here, right? Then, so this is convexity. This is definition of convexity, definition of convexity. So if you accept with that, this, right, is greater, right, it's greater, which is nice, right, which is correct inequality. This minus this is greater than f of this. But this is nothing more than W bar, I'm sorry, the definition, right? W bar, the average of all the previous step, right? That's the average of all the previous step. So by convexity, this is greater than, we're going to keep the expectation intact, right? Is greater than f of W bar minus of W star. And then this is less than or equal to LR over square root of K. So we are done, right? We are done. We can simply replace this with W bar, and the inequality is still home because of the convexity, right? In these directions. So this is exactly what we're looking for, right? On average, F, right? F, the function evaluate at the average of all iterations minus the optimal is less than LR over square root of K. And the left-hand side here, by the way, the left-hand side always positive, right? Why is that? Why the left-hand side always positive? Because we can say, okay, this is minus this less than 1 over square root of K, but so what, right? Let's say this is 0.1, but this is negative 1,000. It doesn't help. It doesn't tell that we converge. Everybody see that? Why this is actually positive? Because F star is the true minimum. F of the minimum is the smallest. So F of W star is greater than F of W star. Right? W star is the true minimum. And we assume F is a convex function. So there's only one minimum. Everybody else is above the minimum. By definition, the minimum. Okay? So this is actually a very nice inequality, because the left-hand side is a positive, and the right-hand side actually converges or becomes smaller and smaller when K is bigger and bigger. So the greater in that sense, right? We can make this error as small as we wish on average as we increase the number of step size. Everybody okay with that? Okay, I'm sorry, we a little bit rushed today, right? A little bit rushed today. I'm sorry about that. But I hope that it's not. You go through on the step again. If you have questions, just let me know, right? It's just a little bit quick, but every step is actually elementary, right? Completing expand them out, adding them up, apply convexity, apply the property of the linearity of the expectations. These are the only thing that we apply. And we also assume, right? We assume that the function is convex. That's the only thing that we assume. So go through that. You have my email. If you have questions, just email me, right? So I'm sorry, it's a little bit longer than we anticipated. I hope that you enjoyed the class. I hope that you learned something. we cover hopefully some basic and important topics in machine learning, right? In particular, deep learning from purely mathematical point of view, right? Of course, we borrow some of the probability theory here, but other than that, you see that we use very elementary mathematics to actually convey, right? To understand why machine learning works, right? And you see that the proof that we do here is actually very simple. We assume that a function is convex, right? In reality, the function is never convex, right? At least it's not globally convex, but there's still one thing that we can hope or assume is that locally it's convex, right? Then our result is actually valid for local, right? But if the function never have anything, actually there's no local minima at all, then actually there's no hope to do anything, right? So this is not, on the one hand, it looks like very, very limited, but you're thinking about, when you do optimizations, right? This is local method. As soon as you go to the Bayesian attraction of some local minimum, the theories actually go through locally. Okay, so it's not that bad. Any questions? Okay, if not, then I hope you have learned something, and if you have any questions, just let me know. Okay, so hopefully I will be back here again to teach you additional stuff later, a year from now, or I don't know. I will talk to Chung Hao and Professor.